This video is going to look at 1.4 energetics for AQA A-level chemistry, focusing on Hess cycles. The video is going to cover a recap of Year 1 energetics definitions, Hess's Law, an introduction to thermochemical cycles, constructing Hess cycles or thermochemical cycles, and calculations involving these cycles. There are a number of definitions for energetics across AQA A-level, both Year 1 and Year 2, but the two most important ones for this topic and at Year 1 are standard enthalpy of formation, delta HF, and standard enthalpy of combustion, delta HC. Now you need to remember that the triangle sign, which is the uppercase Greek letter delta, means change, and the circle with a line through it denotes that the quantity being stated was measured at standard conditions, which you need to know will be 298 kelvins and 100 kilopascals. What that means is that a quantity that's stated with that symbol has been measured at 298 kelvins temperature and 100 kilopascals pressure. And it means that we can compare those quantities, and we can use those and know that our calculations are comparable to others. Now those definitions, delta HC and delta HF, are normally worth 3 marks if you're asked for them in an exam. So I want you to have a think about delta HF and delta HC, pause the video and see if you can come up with the 3 marks for each one. Well, hopefully you've remembered those definitions, and it is really important to learn them. And those definitions, for delta HF, the first mark would be for saying the enthalpy change when 1 mole of a compound is formed from its elements in their standard states at standard conditions. Now we can say, instead of enthalpy change, heat change or heat energy change. But if we say that, we also have to say at constant pressure. Now, that's quite a mouthful, so I would just go with the enthalpy change because that's much more simple. Now, the second definition, delta HC, the 3 marks are for the following. The enthalpy change when 1 mole of a substance is burnt completely in oxygen with all reactants and products in their normal states under standard conditions. Now again, we could say, instead of enthalpy change, heat energy change at constant pressure, if you want to write all that down. And where we've got substance here, that could be compound, element, but substance sort of covers everything. The next thing we can say is that instead of saying burnt completely, we could say completely combusts. They are the same thing, so we could say that. And then all reactants and products, you could say all substances instead of saying all reactants and products, and that would all be the same thing. Now, those definitions are really important to learn, and it would be really nice if in the exam you got a 3-mark question where it asks you to give the definition, 3 easy marks if you've learnt it. But more commonly, you're expected to use the definitions and not just be a parrot spewing out words. You have to learn those definitions and understand them so that you can apply them. And that's why I've gone through them at the beginning of this video, because you need to be able to use these definitions for what follows, the calculations. So I want you to think about the definitions that we've just looked at and see if you can answer the question that's on screen. What is the value of delta HF for O2 gaseous? Now, if you think through the definition, as the definition states, delta HF is the change in enthalpy when 1 mole of a substance is formed from its elements in their normal states at standard conditions. So, we have 1 mole of a substance being formed. Well, the substance being formed will be what we've been given, so delta HF for the O2 gaseous. So, that would be O2 gaseous that we'd write here. And we're forming that. Now we're forming it from its elements in their normal states at standard conditions. Well, what are the elements present in our substance? Well, we have O2, and its normal state at standard conditions is gaseous. So actually what we've got here is O2 gaseous forming O2 gaseous. There is no change. Now, if there is no change, there can be no enthalpy change. So therefore, as we've said, O2 is already an element in its standard state, and there is no change from reactant to product. Delta HF for O2 gaseous will be 0. Now, this is actually true for any element in its standard state. The delta HF for any element in its standard state is always 0 because you're forming an element from its elements at standard states. So I've put it in a yellow box there to show you that it's something that you need to know. It's not a definition as such, but you do need to know it. And a very common question in the exam is, why is the value of delta HF for O2 gaseous 0? Well, it's by definition, delta HF for an element will always be 0. So moving on to look at Hess's law. By now, you should be quite familiar with reaction profiles. Reaction profiles are these graphs that show us the change in energy from reactants to products. Now, normally we'd have a bump in there that shows us the activation energy, but we're not worried about that today. We're not looking at the activation energy. We want to look at specific parts of this reaction profile. And the bit that we're interested in is this bit here. We can see that the enthalpy change for this reaction is the difference between the energy of the reactants and the energy of the products. Now, this reaction we can be even more detailed and say that this is an endothermic reaction. The reactants have got to gain energy, take energy in, because the products are higher in energy, and we're showing this by an upwards arrow with a positive delta H. But again, that's not necessarily what we're really interested in today. What we're going to use these reaction profiles for is to explain something called Hess's law. And as well as being familiar with reaction profiles, you should also by now be familiar with mechanisms and other series of reactions where we might have intermediate steps present. So I'm going to take my reaction profile again, and I'm going to put in an intermediate. Now, the intermediate could be an additional reaction. It could be that the reaction is easier to perform, or they might have a faster rate of reaction, but it is where the reactants form the intermediate and then the intermediate forms the products. Now, that intermediate could be where I've put it above, it could be below. It doesn't actually matter where it goes here. I'm going to put it above just because it makes the diagram clearer. And what we can do with this reaction profile is say that we would need to put energy into this reaction for the reactants to form the intermediate. But then the intermediate would give out energy to form the products. What would happen to the delta H overall for this chemical reaction? Well, even though we've gone through an intermediate, the energy of the reactants and products has not changed. And so delta H for the reaction will be the same as before. Now, if we look at these two arrows, we've got this little downwards arrow, and that will cancel out the equivalent amount of that up arrow. And we will see there that the actual energy change is exactly the same whether we've got an intermediate or not. And this is just to show us Hess's law. So just to put that graph into a slightly different context, we looked at the fact that we had a reaction where the reactants form the products. And I'm going to call that delta HR, the enthalpy change for the reaction. Now, there's no real definition of delta HR. It literally means the enthalpy change for the reaction that's given. The reaction that's given could be a formation, it could be a combustion. It doesn't matter. We just call it delta HR sort of casually. Now, we said that the reactants formed an intermediate, and I'm going to call that delta H1 just for this purpose. We also said that the intermediate could form the products, delta H2. So what we've got here is we've got two routes to go from reactants to products. We can go directly from the reactants to the products, following that simple route, or we can go via this second route, which is slightly longer but might have a higher rate of reaction. Okay, and we can go that second route. We can state then that delta HR is equal to delta H1 plus delta H2, the energy for delta H1's reaction to occur plus the energy for the next one. Now, we are still going to get the same result. Delta HR will be the same whether we do reactants to products directly and measure that, we would get the value delta HR. Or if we go round the long route, we are still going to get the same value, delta HR. And that's exactly what Hess's law is all about. Hess's law states that the enthalpy change of a chemical reaction is independent of the route taken. It only depends on the initial and final stages of the reaction. Now that is a definition that needs to be learnt. You don't necessarily need the bit I'm putting in brackets here at the end. If you're asked to state Hess's law, then you can get away with just saying the enthalpy change of a reaction is independent of the route taken. But I think that the bit I've put in brackets does help with understanding, so I'm going to leave it there. But as I said, really important that you know that. Any chemical reaction at all, the overall enthalpy change will only depend on the energy of the reactants and the energy of the products. It doesn't matter how many other steps you pass through. So on to looking at thermochemical cycles. Thermochemistry is the study of, as it sounds, the interaction between heat and chemicals in chemical reactions, so the interchange between heat energy and chemical energy and that kind of thing. So energetics is thermochemistry. Now thermochemical cycles are also called Hess cycles because they follow Hess's law. And these cycles link chemical reactions together and allow us to do calculations for systems or chemical reactions that might otherwise be difficult to measure. So as an example, we could look at this chemical reaction here. Carbon as a solid reacting with gaseous oxygen to form carbon monoxide. Now this is a reaction that we might want to be able to measure the value of. But if you put carbon and oxygen together, complete combustion will occur. Even if you limit the amount of oxygen, you will get a mixture of complete combustion and incomplete combustion. Now this reaction is for incomplete combustion, and it is not one that we can ever do in a laboratory just producing carbon monoxide at standard states. You will always get complete combustion and carbon dioxide as well. But we might want to know that value and be able to calculate it, and Hess's law allows us to do that. What we do is we take a couple of other reactions as well. The carbon monoxide, if you think back to the blast furnace from GCSE, carbon monoxide reacts with more oxygen and produces carbon dioxide. And also, as I've said, we know that carbon reacts with oxygen to form carbon dioxide as well. Now hopefully what you can notice here is that we've got quite a lot of repetition of both reactants and products. And this is how we build a Hess cycle. I'm going to take this first initial reaction that we've got at the top, and I'm going to write that out again, and this is going to form the top of our cycle. So carbon solid plus half O2 gaseous forms CO gaseous. Now if we look, we've got here CO gaseous, and that actually appears as the reactant for our next reaction. And it doesn't matter what order we're looking at, this is just coincidental that it's one after the other. And this second reaction that we're looking at here tells us that the CO reacts with half O2 gaseous to form CO2. And so I'm going to use that to form a cycle. CO gaseous reacts with half O2, which I'm just going to put with the arrow, and that makes CO2 gaseous. Now, what we've also got here is that this reaction forms CO2. And if we look, CO2 appears exactly the same as the product for a second reaction. And the reaction that we've got here is that carbon solid plus O2 forms CO2. Well, we've got in our chemical reaction, if we look just here, carbon solid and O2 gaseous. Now we don't quite have enough of the O2 gaseous, but carbon solid will react with oxygen to form CO2 gaseous. In our reaction we've got here it's a whole O2, and in this reaction here it's a half O2. So again, I'm just going to put plus a half O2 gaseous next to the arrow to show that it's a condition that we'd need for this reaction to occur. And then what we've got is a thermochemical cycle, a Hess cycle. This is linking together the various reactions that we have. And hopefully you can see that. We've got our first reaction here. Ooh, use the highlighter. So we have the first reaction here, okay, which I'm going to leave in red, which is the one at the top here. We've then got the second reaction, which is the reaction of carbon monoxide to form carbon dioxide, which is the reaction I'm just highlighting just here. And then we have our third reaction, which is the carbon solid plus O2 forming carbon dioxide, which we would have shown in this kind of scruffy way like that. So we've got all three of these chemical reactions linked together in a balanced chemical cycle, or a Hess cycle. And we're going to have a look at another couple of examples of those to hopefully get a good understanding of it. Now, Hess's law can be applied to any chemical system. Absolutely any chemical reaction can be part of a Hess cycle, and Hess's law is a law of chemistry. It applies to everything. So let's have a look at another cycle. Okay, we've got a few more reactions here. Now this might look a bit confusing, but all we've got here is just another extra step. And what you need to look for is you need to look for common substances that appear more than once, because as long as you've got common substances that appear more than once, you can link them together. So hopefully you can see what I'm doing here is that I'm just highlighting where we have common substances, and that will hopefully give you an idea of where we can go with this. Okay, so just take a second to look and make sure that you can see where I've highlighted those and why. So to build a cycle, it doesn't really matter what you start with, but I'm going to start with my top reaction just because it's there. So C2H4 reacts with H2 gas to form C2H6. This is actually the hydrogenation of ethene to form ethane, if you're interested. So we have ethene, which has the double bond, and we add hydrogen across the double bond to make ethane. That's not overly important at this point, but always make sure you're aware of the chemistry that's going on. So that's our first reaction here. Now what we can see is that we've got C2H4 in the reaction that I've just written down, and in the second reaction we can see I've highlighted in yellow both times that C2H4 also reacts with oxygen, and that forms CO2 and H2O. So I'm going to put an arrow here because we've got C2H4 as a reactant, and the products of that reaction are CO2 and H2O. Okay, now I'm going to put alongside the arrow here again, okay, that we've got plus 3O2 because that's what it's reacting with. And if I look here, I've got the products CO2 and H2O. Do they appear anywhere else? Well, we actually do have CO2 and H2O being the products of our last reaction, which if we look is the reaction of C2H6 with oxygen. Do we have C2H6? We've already written that down. We've got C2H6 just here. So C2H6 reacts with oxygen to form the products we've just written down. Now that's 3.5 O2. We'll talk about that in just a second, but I'll just put that against there. Now we can do the balancing, make sure it's balanced. Okay, 2 CO2 and 3 H2O. Now what I've done there is I've unbalanced the reaction of the C2H4 reacting, but this will all come right again in just a second. Now, other things that we've highlighted, we've also highlighted H2, and H2 appears twice. Our hydrogen here is reacting with oxygen to form H2O. Well, what do we notice? We have H2 reacting with oxygen to form H2O, and it's reacting with a half O2. Now, hopefully what we can see now is that we've got 3.5 O2 on the reactant side of that first reaction, And then on the other side, we've got 3.5 O2 just there. And this is an example of another cycle. Now, some people find that a bit confusing having two arrows. So what I'm going to do is I'm actually going to combine these two arrows together. And I'm going to put here the half O2. So this one arrow that we've got here is actually showing the reaction for both C2H4 and H2. And if you want to make that just a bit clearer, we can even move the arrow slightly over so that it's showing that it is just the reactants on that top reaction reacting. And that's another example of a Hess cycle. Now, a third example would be to go through something about enthalpy of formation. Now, enthalpies of formation are very difficult to measure in a lab under standard conditions. If you think about formation of methane, methane would be the reaction of solid carbon, carbon in its standard state, the standard conditions, and gaseous hydrogen. Now, if you put hydrogen and a piece of graphite together, they will just sit there and not react. Okay, it is a reaction that needs a high activation energy. We'd need to give it a spark and set it on fire, basically. So enthalpies of formation are very difficult to measure at standard conditions. And I've got another example of a reaction that's quite difficult to measure here as well, which would be the enthalpy of formation of this alcohol. This is propanol. I'm not being fussy about whether it's propan 1-ol, propan 2-ol. So I've just been a bit lazy here and put C3H7. You should always make sure you actually show the structural formula and not just molecular, but never mind. What we've got here is the enthalpy of formation of this. 3 solid carbon moles react with 4 hydrogen gaseous and half O2 gaseous to make propanol. Now again, if we put a piece of graphite, some hydrogen and some oxygen together at standard conditions, room temperature in a lab, it is not going to spontaneously react together to make propanol. So it's very difficult to measure this. Now other things are easier to measure though. What can we measure? Well, what we can measure very easily is the combustion. Now we can very easily burn substances in a lab. I could put a piece of carbon, set it on fire and heat up some water to measure the energy change that occurs, and we can therefore measure the combustion enthalpy very easily. Now that is studied in a topic called calorimetry, which is part of year 1 energetics, and also is studied at both GCSE chemistry and physics and combined science. So what we can do here is we can combust everything. Okay, we could combust the 3 moles of carbon to form 3 moles of carbon dioxide. Okay, so that would be the delta HC of carbon. Okay, now combustion enthalpy is for 1 mole. We're going to look at this just a bit later. But 3 moles of carbon forms 3 moles of CO2. We can also combust the hydrogen, so we can burn 4 moles of hydrogen, and that would form 4 moles of H2O. Now, when it comes to the oxygen, can we burn oxygen? Can we combust oxygen? Well, delta HC is the definition that 1 mole of a substance reacts completely with oxygen at standard conditions. Well, oxygen added to oxygen at standard conditions would just be more oxygen. So in the same way that the delta HF of elements is 0, there's no delta HC for oxygen because it is reacting with oxygen and we just make more oxygen. So we don't include that in our reaction just here. What we do have though is we can do a delta HC for propanol. If I just put this here, apologies for the mistakes. Okay, and that would also form 3 moles of CO2 and 4 moles of H2O. So we have got another cycle here that we can do using the delta HCs. And I'm going to go through another example of that later in the video in case that hasn't made sense. So I'm going to go on to activity 1, time for you to have a go yourself, and I'd like you to construct a thermochemical cycle or Hess cycle, they are the same thing, for the following sets of reactions. So first of all, for number 1, a little bit general here, we've got a reaction of A and B forming C. C also reacts with B to form D, and then A can react with 2 B's to form D as well. So see if you can link those together in a cycle. Doesn't need to be labelled, but does need to be balanced. And then number 2, this actually is a bit linked to year 2, but I want you to have a go now. Solid silver chloride can dissolve in water to form aqueous silver plus and aqueous chloride minus. Silver plus gaseous can dissolve to form Ag plus aqueous. Cl minus gaseous can dissolve in water to form Cl minus aqueous. And Ag plus gaseous can react with Cl minus gaseous to form AgCl solid. Don't worry about all of those processes. All I want you to do is for both of those sets of equations to see if you can link them together in a cycle. So as always, pause the video, think it through. If you're stuck, go back and look at the previous examples just to give you a bit of a reminder, and the answers will follow. So answers for this one. So this is our general example first of all, and we're going to go with the first equation I'm going to put at the top. Now it doesn't actually matter which one you put at the top of the cycle, they will all end up forming the same thing, but I'm going to go with A plus B forming C at the top. And that's our first expression used, our first reaction used rather. Now we can see here that C also reacts with B to form D. So C forms D. And I'm going to put here plus B, although that's not important, but just to keep it balanced. We could put plus B up here. It doesn't actually matter where we put it. Now, we can see here that D is also formed by A reacting with 2B. So D can be formed by A reacting with B, but we need two B's, so I'm going to put just another B there. And that would be the cycle. So that one's fairly simple. Okay, if you didn't get that one, just go back and maybe have a look at it again. The second one, a little bit more complicated. Again, we're going to go with the first reaction. I'm going to put AgCl solid. State symbols are important for this one. Forming Ag plus aqueous and Cl minus aqueous. And it's a case of looking at the contents of that reaction and saying, do we have any of these things anywhere else? Well, we've got AgCl, which I've just put here, twice in our sets of reactions. We have it as a reactant, as we've already written, and we have it as a product. And I'm going to take that product reaction, this one here, and that's what I'm going to put in my cycle next. The AgCl can be formed by the reaction of Ag plus gaseous and Cl minus gaseous. And there we go. Now, to finish off our cycle, can we join up any other bits? Well, we've got here Ag plus gaseous and Ag plus aqueous, and we do actually have a reaction that links those together. So Ag plus gaseous forms Ag plus aqueous. So we can have that reaction like that. And then we also have here Cl minus gaseous and Cl minus aqueous. Use the highlighter there to make them easier to see. And we have Cl minus gaseous forming Cl minus aqueous here. So we have this reaction that we can go like that as well. Now, again, some people don't like to have two arrows, so we can get rid of that fairly simply, and we can just replace all of that with one arrow, which would be the reactions all together. And just to make that a little bit clearer, what we can do is we can label these just so that we can see what's going on here. If I call this 1, 2, 3, and 4, the reaction that we did first is reaction 1. We then said reaction 4, because the Ag plus gaseous and Cl minus gaseous can form AgCl solid. And then the arrow on the right is the Ag plus gaseous forming Ag plus aqueous and number 3. So it's those two equations together. Now, once you understand Hess cycles, which are quite complicated, but once you've got those sorted out, we need to move on to calculations involving Hess cycles. Now, as I mentioned already, these calculations are to help us work out the values of enthalpy changes that are not directly measurable or not easily directly measurable. So I'm going to go with another general reaction scheme here. A forms B, A also forms C, and C can form B. And we're going to link those together into a quick Hess cycle. So A forms B, and I'm going to call that delta H1. A also can form C, which I'm going to call delta H2. And then C can form B, which I'm going to call delta H3. So we've got 1, 2, 3, and they're linked together in that cycle. Now, if we have two of those values, we can work out the value of the third, and it never matters which value we have. It's all to do with Hess's law. So if we were to look at the first reaction, reaction 1, A forms B, delta H1. Now we said already that the overall enthalpy change, delta H1, is absolutely independent of the route taken. So delta H1 will be its direct value, which we have put in yellow, or we can go the indirect route, which would be the values of delta H2 added to delta H3. So that's the first one that we could work out. If we wanted to work out what the value of delta H3 was, C to B, we can go directly in the route that I've given, or we can go following that second route. So delta H3 can be direct, as I've just said, or we can follow it round the other way. Now, look at the direction of the arrows that I've just drawn. Can you see how, when we go this way around the cycle, I'm actually going in the opposite direction of the arrow that is labelled delta H2? Now, what this means is, instead of adding together the value of delta H2, we would take whatever the value was, and it would be the opposite sign, the negative of that value. So it would be the negative of delta H2, and then we add delta H1 to it. Now, the reason we add delta H1 is because we're going in the same direction as the arrow. So these two arrows would be going in the same direction. So we want to go from C to B. And if we're going against the arrow like we have here, so we're going in the opposite direction as we travel around, we minus the value of the enthalpy change. Now, if we wanted to look at the value of delta H2, for example, just to give another one. So if we look at delta H2, now delta H2 is the reaction of A forming C. Now we can go A to C directly, as I've just drawn, or we can go A to C indirectly, going the long way around. So delta H2 will be equal to either A to C directly or A to B and then round to C. Now, looking at the direction of the arrows, we're going with the direction of the arrow for delta H1, so it would be plus delta H1. Then we're going opposite direction to this reaction delta H3 that's labelled, so we're going against the arrow for B to C. So we'd be minusing the value of delta H3. Now that's not a general reaction as such, okay? This is something that you work out for every situation that you're in. You have to remember that if you're going in the same direction as the arrows, you add the values, and if you're going against the arrows, so if you're going in the opposite direction, like this one, you would minus that value. So we're going to look at an actual example now. So example 1, calculate the enthalpy change of formation of methane given the following combustion data. You may find constructing a thermochemical cycle helpful. Now this is an old exam question. This is one that has come up before. So we're going to approach this like any exam question. And the exam question is asking us to calculate the enthalpy change of formation of methane. It then gives us some data, given the following combustion data. And we've got some nice combustion data just here. We've got the value for the combustion of methane. we have a value for the combustion of carbon, and we have a value for the combustion of hydrogen. Now, exam technique, remember, okay, highlighting just to make information clearer. So I've highlighted that in different colours just to make it so that it's clear in my head. Now, what we've also got is the actual question. It says calculate the enthalpy change of formation of methane. So the first thing that you need to do when you're doing these enthalpy change calculations, the very first thing you need to do is to make sure that you write out the equation that you're being asked for. So we are being asked to calculate the enthalpy change of formation of methane. That's what I'm going to write out. Done it already. C solid plus 2 H2 gaseous forms CH4 gaseous. Enthalpy change of formation, remember, is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states at standard conditions. So methane is CH4, so 1 mole of solid carbon would react with 2 moles of gaseous hydrogen, H2, to form the methane. So that is delta HF, and I'm going to label it as such as well. Now the next thing we're going to look at is the data that we've been given. We've been given combustions. Now, I said at the beginning of the video, you need to know the definitions and apply them. So, delta HC, the enthalpy change when 1 mole of a substance completely combusts in oxygen at standard conditions, standard states, etc. So, I'm going to write an equation. The equation is when 1 mole of a substance, so CH4, reacts with oxygen to form the combustion products. I'm going to make that a balanced chemical reaction. So there we go. There's the balanced chemical reaction for that one. We have also been given delta HC for carbon. Now, delta HC for carbon is the enthalpy change when 1 mole of carbon combusts completely in oxygen under standard conditions, which would form CO2. We've also been given delta HC for hydrogen. Again, when 1 mole of a compound completely combusts in oxygen to form the combustion products. Now, to make this balanced, it would be half O2. So those are reactions to show the combustions. Now, in the same way as the rest of the thermochemical cycles that we've done, we need to link these together. So the first thing I'm going to say is we've been given delta HC for methane. So I'm going to use that, and I'm going to add this to my cycle. Delta HC for methane would form carbon dioxide and water. So I've got here CO2 and 2H2O, CO2 and 2H2O. So what we've got is the chemical reaction. I keep pressing the wrong button. So we've got, and again, don't want it red, we want it yellow. So we've got this chemical reaction just here, which is that yellow chemical reaction that we've written down to begin with. Okay, it's written in a slightly strange format because it's on its side, but we have the reactant CH4, and we have the products CO2 and 2H2O. Now the next bit of this cycle that we can look at is we're going to say the delta HC for carbon. So delta HC for carbon would be the reaction of carbon to form CO2. Now also on that arrow we can include this blue reaction that we've got written down here, because the hydrogen will also combust to form water. So I'm going to label that just there. Now, looking at definitions, these equations that I've written down at the top here are all according to the definition for delta HC, which is for 1 mole. And we do have 1 mole of carbon and we have 1 mole of methane, but we have 2 moles of hydrogen. So this would actually be 2 lots of the value of delta HC for hydrogen, and that's because the definition tells us that delta HC is when 1 mole of a substance combusts and we have 2 moles. So we'd have to take that into account twice. Now this is our balanced chemical equation. One thing people might think is, well, hang on, where's the oxygen? Okay, we've got no oxygen at the top here, and all of a sudden we've got oxygen appearing at the bottom. Now this is absolutely spot on okay, because we've got these arrows being delta HC, and by definition delta HC is about combustion with oxygen. So we don't need to add oxygen anywhere in the cycle. Labelling it as delta HC brings in the oxygens that we would end up with down at the bottom. So how do we do a calculation for this? Well, we want to work out delta HF for methane. Delta H, not A, so delta HF for methane is what we want to be finding out. So we are going to be going, we want this direction, but we are going to be going this way around the cycle. So delta HF will be equal to, if we look at this cycle, this arrow here, I'm going to put this in green now, so we're going to go this way first, so it's going to be everything that arrow means. And we can see here that that arrow is delta HC for carbon added to 2 lots of delta HC for hydrogen. Then we come up the other side of the arrow, and we're now going in the opposite direction to the arrow that's actually there. So what we're going to be doing then is we're going to be taking away the value of delta HC for methane. So just have a look at what I've just done there. Okay, we want to go from left to right on the top equation, so we're going to follow it around that way. Okay, so look at the direction of the arrows. So plus delta HC for carbon, plus 2 lots of delta HC for hydrogen, minus delta HC for methane. Now I'm going to put the values in. Okay, looking at the values we've been given, delta HC is minus 882. So I'm going to put these in brackets. Got myself completely muddled there. I'm not going to start with with this value just here. Apologies, speaking in tongues. We're going to start with the value of delta HC for carbon, which is this one. So apologies. I'm going to put that in brackets. So because it's a plus here, I'm going to put this in brackets, minus 394. Putting the value in brackets, keeping it separate from the operator in the equation, just to make sure that we don't confuse anything. We're then doing the 2 delta HC for hydrogen, because we're going that way around the circuit. So we have here the value of minus 286, but it's a plus just here. So plus 2 times minus 286. Okay, so again, we're keeping those operators separate, okay, from the signs for our values. After we've done the hydrogen, it is minus the value of methane. Now methane is minus 882. Now, when we put that to our calculator, what we'll end up with is minus 394 minus, it helps if I have my calculator, get that to hand, 2862. So minus 572 minus a minus, which is plus 882. So that's how we'd solve that one. And putting that all into a calculator would come out with the answer minus 84 kilojoules per mole. Okay, we're going to look at another example, and hopefully I'll make this one a bit clearer than the previous one. So example 2, calculate the enthalpy change of combustion of methane given the following data. You may find constructing a thermochemical cycle helpful. Now, initially this might look exactly the same as the previous question. However, what we've got here is we are being asked to calculate the enthalpy change of combustion of methane. And we've been given delta HFs this time. Now again, I'm going to do what I did before. I'm just going to highlight the data just so that it's clear. For me, you don't have to highlight this in the same way, obviously. And the first thing that we always need to do for an enthalpy calculation, okay, first of all, it says you may find constructing a thermochemical cycle helpful. You don't actually have to, but it is always good practice to do so. We find that people make far fewer mistakes if they do the cycle. So that's what we're going to go forwards with. It's much easier for year 2 as well. But yes, the first thing we have to do with any of our cycles is to write an equation for the top of our cycle that covers the equation we're being asked for, which in this case is the combustion of methane. So remembering our definitions, enthalpy change when 1 mole of a compound is completely combusted in oxygen at standard conditions, etc. So that would be CH4 plus 2O2 forming CO2 and 2H2O. and I'm going to label that as I did before, delta HC for methane. So that's the target, that's what we want to end up calculating, that's what we're trying to actually find at the end. So that's what we need to put at the top. Now the data we've been given is delta HF. Now delta HF is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states, etc. So CH4 would be formed from 1 mole of solid carbon and 2 moles of H2 gaseous, which you've said already. We've also got delta HF CO2, so that will be the enthalpy change when 1 mole of CO2 is formed from its elements in their standard states, at standard conditions. And also we've got H2O, 1 mole of H2O formed from its elements, in this case H2 gaseous and O2 gaseous. So those are our chemical reactions that we've got. Now when you're answering these questions, you don't have to write those out first, as I have, but this is just to show you where this is all coming from. So, building our cycle then, the first thing we're going to look at is we've got the enthalpy change of formation of methane, just given here. So I'm going to put that on the left of my cycle, an arrow going up, forming methane, because we're going from the elements to methane. So it's going to go up, and I've labelled that delta HF CH4. Now the other thing we've got on this left hand side of the equation is O2, and you may notice that we've not been given a value for O2. Can you remember why? Well, that is because it would actually be 2 O2 gaseous forming 2 O2 gaseous. There is no change, and remembering that the enthalpy change of formation for any element will always be 0 in its standard states. So we don't need to worry about putting it there, we just leave it blank. Now the other information we've been given is the value for the formation of CO2, which would be the carbon reacting with the oxygen, only one oxygen. But we've also then got the formation of H2O, which would be where the H2 and the O2 react together. Now I've already pre-labelled this, and I've already put 2 lots of delta HF for H2O, and that's because we are forming 2 moles of H2O at the top there. Okay, so 2 moles of H2O being formed, so we need to take into account the 2 lots of delta HF, because the definition tells us it's 1 mole only. Now that is our thermochemical cycle, fully labelled, completely balanced, right numbers of oxygen everywhere. And what we're going to do is we're going to look at the reaction we actually want to find out. We want to calculate delta HF, which is for the purple arrow that I've just put in. And we are going to go the opposite way around the cycle. We're going to go the long route. So what's the working for this then? Well, we want to work out delta HC for methane, and looking at our route, we're going to be going this way around first. So we're starting off going in the opposite direction to the delta HF for methane. So this is going to be minus delta HF for methane, because it's the other way, the other direction, the opposite way to the arrow. Then we're coming up with the arrow on the right hand side. So we're going to add the value of delta HF for CO2. My arrows and my brackets keep going a bit strange. We're also going to add, because we're going in the same direction, 2 lots of the value of delta HF for water. Now substituting our values in, delta HF for methane is minus 74.9, but we have a minus just here already, so it's going to be minus, for the operator, brackets minus 74.9. So we have the negative for the opposite direction to the arrow, and then we have a negative for the value of the delta HF. Then we're going to add that to the delta HF for carbon dioxide, which is minus 394, so brackets minus 394. And then we're going to add 2 lots of the value of the formation of H2O, which is minus 242. Now, just to make that a little bit clearer, minus 74.9 would be plus 74.9. minus 394, because we have plus minus would be a minus, and then we have plus 2 lots of minus 242. So 242 times 2 is 484, but we have a minus here because it's plus and minus. So putting that all into the calculator, we would come out with a value of minus 803.1 kilojoules per mole. A little bit out with the significant figures here, we probably just should put that as minus 803 kilojoules per mole, 3 significant figures to match the data in the question. And that's our second example. So it's always a case of writing out the working first, always write that out using the labels from your equation and then substitute the numbers in. Now if you are asked to work out any of the other values, if you are asked to work out delta HF, for example, for CO2, then we would just move these to the opposite side and they would become the other arrow. But if you've drawn out the cycle, then you'll be able to see that from the very beginning anyway. So, activity 2, given the following data, delta HF for methane, delta HF for chloromethane, and delta HF for HCl, calculate delta H for the reaction of methane plus chlorine forming chloromethane and HCl. And the second question, calculate the enthalpy of formation of butane C4H10 using the following data. The enthalpy of combustion of graphite, the enthalpy of combustion of hydrogen, and the enthalpy of combustion of butane. Now for both of those, I want you to draw a cycle and then show full working as I did on the previous 2 examples. But as always, pause the video and the answers will follow afterwards. Right, activity 2 answers then. Question 1, given the following data, delta HF for methane, delta HF for chloromethane, and delta HF for HCl, calculate delta H for the reaction. So first of all, I'm going to call this delta HR, because it's not a specific reaction that we're looking at. I'm just going to call that delta HR. And we've been given the data that we can see on screen, which I am just going to have a look at a bit more closely. So delta HF for methane, well, we know that delta HF is the formation of 1 mole, so we are forming 1 mole of methane and we're forming it from its elements in their standard states. Now I'm not going to worry about putting state symbols in there, but I'm just going to get my balanced equations sorted out. Chloromethane, forming a mole of that, so that is being formed from a mole of carbon, a mole and a half of H2 and half a Cl2, small there, and then delta HF for HCl is going to be half an H2 plus half a Cl2. Okay, so those are our equations. That's what we've got to think about. It doesn't necessarily need to be very neat, that's just working. So looking at our cycle then, or building a cycle, we've got here methane, and we've just said that we have delta HF for methane. So what we can do is we can form methane, which means that we're going up with the arrows, and we're going to form that from a mole of carbon and 2 moles of H2. Okay, now we're going to label that delta HF CH4, just so it's clear. Now we've also got the chlorine here, but chlorine, well, that's already an element, so that would be just the same as it is down at the bottom there. You can see we've got no value for chlorine up the top, that's not there, and that's because, as we've said before, that is 0, so we don't need to worry about putting that into our cycle anywhere. On the other side we have the CH3Cl, so we're forming that, so we have delta HF for CH3Cl, which we can see from up here is 1 carbon, 1.5 hydrogens and half a Cl2, and then what we have also is we have the delta HF for the HCl, which we said is half an H2 and half a Cl2, and if we add those together, if we were to look at everything on, or everything in that circle that I've just drawn, that would be equal to 1C, 2 H2s and a Cl2, so that is sorted just there. So we want to find out delta HR, that's what we want, so we are going to go round the cycle. Instead of going left to right like that, we're going to go round the cycle in that direction. So following that round, we are first of all going to be going down this way, and so we are going to be doing minus delta HF for methane, because it's the opposite direction to the arrow. And then we're coming back up this side, so we're going in the same direction as the arrow, so we're going to add delta HF for HCl, and we're going to add delta HF for CH3Cl. Substituting our values in, we have the minus of the delta HF for methane, which is minus 74.8, remembering that we're keeping the operator, the mathematical operator, separate from the exo-endothermic sort of inferring sign. We are then going to add the delta HF of HCl, which we can see is minus 92.3, and then we're going to add the delta HF for the chloromethane, which is minus 134.5. So minus and minus becomes plus 74.8, plus and minus is minus 92.3, and minus 134.5. And when we pop all that into the calculator, we get an answer of minus 152 kilojoules per mole. And the answer to question number 2, calculate the enthalpy of formation of butane using the following data. So we have the enthalpy of combustion of graphite, we have the enthalpy of combustion of hydrogen, and we have the enthalpy of combustion of butane. So these are all delta HCs. Graphite is pure carbon, so this would be delta HC of C, and the combustion of that would be carbon plus oxygen forming CO2. Hydrogen we know is H2, and the delta HC of that would be H2 plus O2 forming H2O. We only want 1 mole of one mole of the H2 to react, so we're going to need half an O2. And then for butane, it's going to be delta HC for C4H10, and that will be C4H10 plus O2 forming 4 CO2 and 5 H2O, and we are going to need for that then quite a lot of oxygen, but we don't really need to worry about it, which we'll talk about in just a second, so don't worry about balancing, that's not necessary. So the question that we're looking for, formation of butane, first thing we need to do is an equation for that. So we're forming butane, C4H10, we would form that from 4 moles of carbon and 5 moles of H2, so that's our formation. We're then going to be combusting the graphite, so we're going to have 4 lots, because it's 4C, of the delta HC for carbon to make 4 CO2. That's why we don't need to worry about the oxygens, remember, because it's taken into account with the label for delta HC. And this is also going to take into account, this arrow, our 5 delta HCs for hydrogen. Okay, which, as I said, you can do a separate arrow there, you can have 2, but some people find that confusing when we're following the cycle, so I'm going to put 1. Make sure I add the 5 H2Os at the bottom there, forgot my products. On the right hand side, C4H10, that is the delta HC for butane. We only need 1 of those because it's 1 mole combusting, so it matches our definition. And that arrow goes down, and you can see that everything matches up and it's all nice and balanced. So we want to work out the delta HR here, going in that direction, going here, so we're going to follow it going around this way. So delta HR is going to be equal to everything on the left that added together, so 4 delta, missed out the delta as well, going well. So 4 lots of delta HC for carbon. We're going to plus that to 5 lots of delta HC for hydrogen. And then we're on the other side of the arrow and we're going opposite direction, so we're going to minus the delta HC for butane. So putting our numbers in, we've got 4 lots brackets, 4 lots of the graphite, which is minus 393.6. We're going to add that to 5 lots of the delta HC for hydrogen, which is minus 285.9. And we're going to minus the combustion of butane, which is minus 2877.1. Popping those into our calculator, we get 4 lots of minus 393.6 being minus 574.4. 5 times minus 285.9 is minus 1429.5. Remember, plus and minus is a minus. And then we're going to add, because it's a minus, 2877.1. And when we put that into the calculator, that comes out to be minus 127 kilojoules per mole. And that is to 3 significant figures.